Just last minute
Last minute?
stuff. I mean, almost done. Just
Oh, okay.
checking.
So that's good. That's good. It sounded like you're reserving it for the last minute.
No.
Which would mean that I made it too easy, right?
No, not really.
It wasn't too hard, was it?
No, it was good.
It is lengthy, very lengthy.
It's long. Okay. You're at 4 weeks. So. Okay, so let's get started. So last lecture we started talking about integer multiplication, and we'll try to finish up that discussion today. Okay, so integer multiplication is really a very interesting problem, and the algorithms we'll discuss today are among the most interesting algorithms that we will discuss in this course. Right? So it's really fascinating how people can, make connections between things that we don't connect normally, and use that connection to find very efficient algorithms for a very old problem. So that's what we are going to try to do, and there are a few related multiplication algorithms, and there is a unifying way in which we can bring all those algorithms together and understand them as an instance of one general technique, and that's what we're going to try to do. So we looked at this last time. Are there any questions? No questions. Good. So we'll move right along. So now there is a more general algorithm that goes beyond Karatsuba that's called Tomb-Cook algorithm. Right. So it was originally described by Andre Tomb, and then the description was improved by Stephen Cook, I guess, and then that is why it's called Tomb-Cook multiplication. So whereas Karatsuba, you just divided a number into two parts and did the multiplication. Here you're going to divide it into n greater than 2 parts. Okay, and that's what you're going to do. Okay. So the way we are going to generalize is by making the association between, or the connection between polynomials and integers, right? So when you have an integer represented using digits a(n minus 1 through a0, where a0 is the least significant digit, and a(n minus 1 is essentially the nth digit or the most significant digit, right? So, and this is over a base t, right? Where base could be 2 for binary number system and 10 for decimal number system, right? So now a number represented in this way can be viewed as a polynomial, right, of this form, right? So for instance, we have a number 105 in decimal, right? So that is equivalent to saying 1 times 10 square plus 0 times 10 to the power 1 plus 5 times 10 to the power 0, right? So this is how we understand, when we write down a multi-digit number, this is how we understand their value or their meaning, right? So that represents nothing but a polynomial. This can be thought of as an instance of the polynomial x squared plus 5, right? So this can be thought of as a polynomial a of x equal to x squared plus 5, and the value is nothing but a of 10, right? So we substitute the variable in the polynomial by the base, and that gives us the value of that number, right? So this is how we can think of this number as this polynomial a of x, which is summation 0 through n minus 1 ai x to the power I. Okay? So now if you think about how we do polynomial multiplication, right? Let's say we want to multiply x plus 1 right? So how do we do this? We multiply each of these by each of these digits, right? Each of these terms. So you get
3x plus 1.
So that will be
3x
x plus 1 times x squared plus x plus 1 times
2x.
2x plus x plus 1 times 3. Right? So what we are in effect doing is multiplying think of each of these terms as a digit of a number, right? So what we are doing is we are taking 3 and multiplying each of the digits here by the least significant digit here, right? That is this term. And then we are taking the second digit from here and multiplying each of these by the second digit, and then multiplying each of the digits there by the most significant digit, right? This is exactly how we do long multiplication by hand, right? So there is an exact equivalence between integer multiplication and polynomial multiplication, and this is exactly what we are going to rely on. Okay, so essentially the idea is that if you want the product of two n-digit numbers, then you can take the polynomials, you can multiply the polynomials, and then do the substitution of x equals d, right? Right, x is a variable on which the polynomial is composed of, and then you set that variable x to the base d, and that gives you the value of the product. Okay? Now that we see the association between multiplication, integers and polynomials, let's revisit some of the basic properties of polynomials. Okay? The first one is, how do you evaluate a polynomial efficiently? Right? So there is this rule called Horner's rule, right, which factorizes the multiplication involving x, right, so that you can compute it more efficiently, right? So what is the complexity of this Horner's rule computation? Again, let's assume that additions are free and multiplications are the ones that you have to count. So how many multiplications are there when you evaluate a polynomial using Horner's rule? Okay, so near each, after each AI, there is one instance of x, right? So that means there are n coefficients, then there are n multiplications, correct? So it tells you that Horner's rule allows you to calculate an nth degree polynomial using order of n operations, or let's just say O of n, or just exactly n multiplications. If you did it, if you evaluated the polynomial naively, how many multiplications would you use? N squared, right? Because obviously, just to compute an x to the power n, you will already have n multiplications, right? So there will become n squared multiplications if you do it naively, but by using Horner's rule, you're getting n minus just n multiplications total. Okay. Now, the other set of properties that we want to talk about are that an nth degree polynomial has exactly n roots. Okay. Note that we are not saying n real roots, right? But if you are willing to consider both real and imaginary roots, there are exactly n roots for an nth degree polynomial, right? And because of that, you can express it in this form, right? So xi minus ri, where ri is the ith root. So you can also have a third possible representation of a polynomial, which basically consists of xy paths, right? So you say for this value of x, this is the value of the polynomial, right? So you just say, so if you think of the polynomial as representing a graph, if you choose n plus 1 points, right, that will uniquely define the curve. Okay, so as a result, you can represent a third way of representing a polynomial is as n plus 1 xy path, right? Okay, so now what can we do? So now let's look at the, because again we are interested in multiplication and maybe addition, so let's look at how easy it is each of these operations in using these representations, right? So the direct representation is a coefficient representation because we are able to take a number written this way and immediately say what the coefficients are, right? So A2 is 1, A1 is 0, A0 is 5, right? So we are able to look at the digits and immediately read the coefficients. So that is the most convenient way to go back between numbers and polynomials. With that representation, we can do additions easily, right? Because we simply add the coefficients for the same degree, right? So in this case, for instance, if you wanted to do addition, then we know that for x squared, okay, the coefficient is going to be 1. If you want to add these two, again, we look for the coefficient of x, then we add 2 and 1, so 3. And similarly for coefficient 0, 3 plus 1, 4, right? So we can do addition very efficiently if you just keep the polynomial using their coefficient or the most common representation, okay? Multiplication is n squared, right? Because as we said, you have to multiply each digit here by every one of these digits, and then you have to do the addition, right? So there are n digits. Let's say there are n digits in both of them. That means, every combination of those n digits have to be multiplied. So you have n squared choices. So you have to do n squared multiplications, right? So you can see that multiplication using the coefficient representation is inefficient, right? And of course, we know that when we do longhand multiplication of two n-bit numbers, right? So we again spend n squared time, right? So that's what we want to try to avoid. You can try to do that with roots. With roots, multiplication is easy. Addition is quite difficult. Okay, so but I won't go into that. Multiplication being easy is very, very obvious, right? So if I have product of xi minus ri, which is the one polynomial, the other polynomial is another product xi minus, let's say, qi, right? Then the product is simply, you just write these things together, right? So it's product requires really no effort. But addition is difficult because, well, how do you, go from, essentially this is going to, it looks like the only way to go from compute the sum of these two is to evaluate this to the coefficient form and then add, right? Only that seems to be the only way to do it. And that's inefficient. And because of that, well, besides given a coefficient representation, finding the roots itself is quite difficult, right? So it's not like there isn't a straightforward way to evaluate roots of a polynomial accurately and efficiently. So let's just ignore this roots and let's come back to points, right? If you talk about point-wise representation, then both addition and multiplication are easy, right? Because let's say we have a polynomials a of x and b of x, right? So if you represent this as, let's say we evaluate it at 3 points, let's say a0, a1, a2, right? And similarly, we have b of 0, b of 1, b of 2, then you want a of x plus b of x, right? So obviously you can evaluate a of x at the point 0 and then evaluate b of x at the point 0 and you can simply add it, right? You don't have to do the polynomial addition first and then substituting the value of x, right? You can substitute the value of x and then do the addition, right? So as a result, the substituted values are already available here, right? So you just have to do a0 plus a0 right? And of course, when I said you can do the operation before the substitution or after the substitution, it didn't matter what the operation was, right? So if I had a multiplication here instead of plus, still it would apply, right? Which means that once I have this table of values, right, point-wise addition and point-wise multiplication will have the effect of actually adding or multiplying the polynomials, okay? So the point representation is very beneficial because once you have the points, you can do both addition and multiplication efficiently, okay? So that looks like a good strategy. Let's go to the point representation and then we don't have to do n square multiplication anymore. We'll just do n multiplications, okay? But unfortunately, to convert from coefficient to point representation, the most straightforward way to do it is so we know that the polynomial of degree n needs n plus 1 points, right? So you have to evaluate this at n plus 1 points, right? So this is going to be, so we know that even using the honors rule, each evaluation takes O of n multiplications. Now if you have to evaluate it at n points, right? So n points, each of them requiring n multiplications, you have n squared time, right? So yes, we can do addition and multiplication efficiently, but unfortunately, because the conversion to point representation requires a lot of multiplications, we don't seem to win, okay? But of course, if we were trying to design these algorithms, we wouldn't even have seen this connection, right? But if we did see the connection somehow, we still will say, oh, you know, there is this stumbling block, so there's no way, yes, I can do well once I get to that representation, but since going to that representation is going to take n squared time, this is not a fruitful approach. This is not going to go anywhere, okay? So obviously that's why, you know, we are not, you know, the famous people, and the famous people had better ideas, right? So what did they do? So to understand what goes on here, it's useful to use a matrix representation, right? So I just gave you an idea of how to calculate, right, the sum or product of two polynomials using pointwise representation, right? But the point is that finally, when you are done, you want to go back to the coefficient representation because that's what you understand, right? So you can do the multiplication, but finally, if you just give me a bunch of, you know, A0, A1, that's not how I understand a number. A number has to be, you know, something like this. So let's try to understand in a more precise way what it means to evaluate the polynomial at certain points, do a point-wise multiplication, and then come back to the coefficient representation again. Yes?
I'm really sorry about this, but again, that slight sound is making it like hard to concentrate.
Sorry.
Yeah.
I don't want to
sorry,
distract you from this.
I'm slightly sensitive about it, but
Okay. I'll not.
Okay, so okay, now, so these are, so you have the polynomial a of x, which is, you know, atx to the power n, not n, atx to the power t, right? Okay, so yeah, that's a typo, x to the power t, okay? And you can, you want to evaluate it at n points, rather m points, yeah, m points, x0 to xn, okay? So I'm decoupling. You know that m should be at least, you know, n, right? Or n plus 1 actually, in order to uniquely define this polynomial. But nothing prevents you from evaluating it at more points, right? That's fine. So when we say that a polynomial is uniquely defined by its value at n plus 1 points, you are free to represent it using more than n plus 1 points, right? You can represent it using 2n points if you want. That's fine. Nothing is wrong. It's just that it seems like you're, you know, remembering too many points and you might be doing unnecessary work, right? So that's, but so let's decouple. Now we can say that evaluating the polynomial at x0, right? So if you look at this, multiply this row with this column, you'll get a0 plus a1 x0 plus a2 x squared all the way through an x to the power x0 to the power n minus 1, right? So rather an minus 1 times x0 to the power n minus 1, right? So this is the evaluation of the polynomial at the point x0, correct? So this multiplication of this row by this column is going to generate one element in the output matrix, which is going to correspond to the evaluation of this polynomial at the point x0, right? So this value, the value of the polynomial at x0, we are going to call it p0. Similarly, this row evaluates the polynomial at the point x1, and the result we are going to call it p1, right? And so on. So we can write it as a matrix, and you'll see in the next slide why that helps, okay? So again, we haven't said anything new here about whatever we said here about how you can do the calculations and so on are all the same. Whatever we said about how you evaluate the polynomial at a given point hasn't changed. We simply wrote this whole thing down as a matrix equation because it just simplifies something else in the next slide. Okay? So we just say that, okay, there is a matrix representation. So that allows us to talk about it this way. So let's a of x and b of x be polynomials representing two numbers, right? And then we evaluate the polynomials at the chosen points x0 to xn, okay? And so we can say p equals xa and q equal to xb, Okay, so what is this boldface X? This boldface X is this matrix. Okay, so the capital P represents this column matrix, the capital A represents this column matrix, and the boldface X represents this matrix, right? And notice that the way we obtain this is by taking x0 and then writing out its powers in the first row. Taking x1, write out its powers in the second row, and so on, right? So now we can see that there is a sort of a mechanical approach for generating this boldface X, okay? And once you mechanically generate this boldface X, then you can multiply by that column matrix, and that gives you the resulting column matrix, which is the value of the polynomial A at each of those points. Similarly for the polynomial B, that is the other number that's involved, it's again the same X, right? Because you're going to evaluate it at the exact same points. So Q equals XB. Now we want to do pointwise multiplication, right? So we want to do the pointwise product, which we will call as R0 to Rm. So R0 is P0 times Q0, R1 is P1 times Q1, all the way to Rm equals Pm times Qm, right? So just like here, we are doing pointwise operation. Okay, so we are done with that pointwise operation, and so we have R, right? Now, we want to regenerate the polynomial from the point representation, right? So originally what we did was we had a coefficient-based representation. We converted that into point representation by multiplying by this matrix. Now, in this point representation, we did all the multiplication, and now we want to get back to the coefficient representation. So how do we get there? We apply the same equation, right? So we know that this R is obtained by evaluating this coefficient matrix, right? Coefficient polynomial at the same points x0 through xm. So we just put this here, R equals xc, and now we can apply our inverse. So if you multiply, if you left multiply by x inverse, x and x inverse will get cancelled, so you get c, and so you get x inverse times R is going to be your final coefficient. So this x inverse R will give you C, which basically is another column matrix that contains the coefficients of the product polynomial. Okay. So now let's say why are we doing this M? So the point is that if you multiply two degree n polynomials, right? So the degree of the resulting polynomial is going to be degree A plus degree B. Correct? Yes. So let's say if this was an nth degree polynomial and this was an nth degree polynomial, the result is going to be a polynomial of degree 2n, right? Which requires 2n plus 1 points, right? So that's why, even though to uniquely define this polynomial, we only needed to evaluate it at n points, but for the product polynomial, we need something like 2n points, right? So what we do is, at the first step itself, we evaluate this at 2n points. Okay, that's why I have an m that's distinct from n. Okay, so this is a very simple thing. If you don't want to think about it, you can just, because we understand things in sort of layers, and at some level you can say, this is something that I can, worry about later, right? But if you feel like thinking about it, then the point is that this number, right, the number of points you should evaluate should be equal to something like twice the number of digits in the original number. Okay, something like that. Okay, otherwise you'll have an overflow, because otherwise what you will get is you will get the the least significant n digits of the product, and then you will miss everything else. Okay, so something like that will happen. So you don't want that. Okay, so now now we understand, all we have done now is we have systematically understood how to use this point representation, okay? And how we go from coefficient representation to point representation, do the multiplication in the point representation, and then come back from there to, again, the coefficient representation. We have seen that in a precise way so far, okay? So now, the problem though is that we still have not addressed the question of what is the complexity, okay?